Hello, this is the lesson on 7.4 hypergeometric distributions, the last lesson of chapter 7, and let's start. Oh, you don't see anything. Wait a second, how come you don't see anything? Okay, I think it's working. Hopefully it's working. Okay.
Yeah, we can see it.
You can see it, but hopefully it's still recording. Okay. Yeah, it's recording. Okay, I just wasted 40 seconds. Okay, so recall that a binomial distribution has a specified number of independent trials in which the outcome is either a success or a failure. The probability of success is the same in each trial. The outcome of one trial does not affect the probabilities of any other of the later trials. Unlike binomial distributions, hypergeometric distributions, it's a complicated name, but it's actually pretty simple, involve a specified number of dependent trials, and so the individual outcomes cannot be repeated within these trials. With hypergeometric distributions, the probability of success changes on each trial as each trial is made. Each selection reduces the number of items that could be selected in the next trial. It's basically like taking cards out of a deck. As you continue to take cards out one at a time, the probability of getting, let's say, a spade would be changing depending on whether you pulled out a spade or another club, another card out of the deck. The probabilities change as you're pulling out cards, and not replacing them. The key thing is you're not replacing them. So, like binomial and geometric distributions, each trial has two possible outcomes, success or failure. And like binomial distributions, the random variable is the number of successful outcomes in the specified number of trials. All right, let's just do a little Q&A here. Classify the following as either binomial, B, hypergeometric H, or uniform distribution. Recall that the outcomes of a uniform probability distribution all have the same probability. Okay. So the number of clubs drawn from a deck. Let's say you draw one card. Take a look at it, then draw another card, and draw another card. So what would be the distribution of the number of clubs drawn from a deck? Would that be binomial, hypergeometric, or uniform? What do you think? Okay, well, I'll just give you the answer then. It's hypergeometric. Okay, let's say there's only two variables, two outcomes, either a club or not a club. So there's only two options, club or not club. And the probability of getting a club each time is different, because as you pull out cards, the probability of getting a club on the second card, initially it's out of the first one, it's 13 out of 52. 13 clubs out of 52. And if you drew a club, then it'd be 12 out of 51 on the second one, or if you didn't draw a club, it would be 13 out of 51 on the second one. But either way, the probability changes each time. So if the probabilities change and aren't constant, it's hypergeometric. B, the number of people that are born on a Monday in a class of 40 students. So what do you think? If I select people out of the class, does the probability of being born on a Monday change at all?
No.
No. What's the probability of being born on a Monday? If you were going to guess, it would be
1 out of 7.
1 out of 7. And you would, that should, even if you would take people out of the class, everyone should have 1/7 probability of being born on a Monday, right? It doesn't change as you pick people out of the class, right? So that would be binomial. The number of red Smarties randomly drawn from a handful of Smarties. Again, as you're picking Smarties out, do the probabilities change?
Oh, it would be hypergeometric.
Yeah, the probabilities change.
Yeah.
The number obtained when rolling a die.
No.
So
Uniform?
Uniform. They're all 1/6. Yeah. The roll of a 1 in the repeated rolling of a die. You roll.
Binomial?
Yes, because it's always 1/6. Right? There's only two outcomes. Either it's a 1 or not a 1, right? So how does it differ from D? In D, there's 6 outcomes, but in E, there's only 2. It's either a 1 or not a 1, and it stays the same. Right? F, the number of left-handed people selected from a group comprised equally of left-handed and right-handed people. So you know, let's say there's 100 people and there's 50 left-handed and 50 right-handed, and then you start selecting.
Uniform?
No. No. So it's kind of like cards in the deck. If we know for sure that the initial group was 50% left-handed and 50% right-handed, right? Like half and half. When we start selecting people, let's say the odds of being a left-handed person being selected changes after that first person is selected, right? Let's say you pick this. Let's say there was 100 people, and you had 50 left-handed and 50 right-handed. You pick a left-handed person. The odds of getting a left-handed person on the first one is 50 out of 100. But if you pick a left-handed person, the odds of getting a left-handed person on the second try is going to be 49 out of 99. It's not the same as 50 over 100, right? So it would change. So it would be hypergeometric. The probabilities change, not constant. The number of
where does it explain what uniform is?
Oh, I think we did it when we first the 7.1. We talked about uniform distributions. If you look at your notes for 7.1. G, the number of left-handed people selected from a group from the general population. Does are F and G the same, or are they different?
Oh, uniform. Nope.
Well, there's only 2 possibilities, either left-handed or right-handed, right? So if there's only 2 possibilities, it's binomial, right? Uniform would be more than 2, but binomial is just 2. The number of 3's produced by a random number generator. So it's either a 3 or not a 3, right?
Binomial.
Yeah. The number obtained by a random number generator. So let's say that spits out just a single digit, like 0 to 9.
Uniform.
This would be uniform. Okay. The reason it's not binomial because you have 10 outcomes instead of 2 outcomes. You have 10. All right. So let's do an example. And I think this is actually hypergeometric distributions are stuff that I think you already know how to do. Let's look at an example. In a civil court trial, there are 6 jurors. Determine the probability distribution for the number of women on a civil court jury selected from a pool of 8 men and 10 women. Right? So I think you guys already can do this before even teaching 7.4. I think you know. So let's just see. So what's the lowest number of women that could be selected? So we have 8 men and 10 women. We're selecting 6, right? So we could have no women on the jury. We could have 1. We could have 2. We could have 3. We could have 4. We could have 5. Or we could have all 6 women being all 6 members being women, and that's it. We're not selecting any more than that. So what's the probability of no women being chosen? Well, you guys know how to do that. We did this in the previous unit chapter 6. We did this. So let's select the women. How do you select the women?
Oh, wouldn't you do wait, never mind.
How many ways can you select 0 women out of 10? For this, do you want me to use the C notation or just the bracket notation?
C.
The C? Okay. So how many women do we have?
Oh, it's 10 choose 0.
Yeah, 10 choose 0. That's the women. Now we have to choose the men.
And 8 choose 6.
Okay, that's the total ways that we can select 0 women.
You multiply the 2, right? 6?
Yeah, but that's the number of ways. But what's the probability? Well, don't you have to do one more thing?
Oh, you have to exponents.
Oh, no. So it's 10
fine.
choose 0, 8 choose 6. But isn't there isn't it a
Over.
fraction?
It's over,
Over the total?
Yeah, what's the total number of ways you can select 6
Six
people?
choose
6 choose 6?
Nope.
No.
Oh,
So close.
almost there.
Is it 6 choose 18?
18
Well,
choose 6?
yeah, you can't have 6 and
Yeah.
choose 18. The bigger number's got to go first.
That's what I meant.
Yeah. Okay. And that equals, if you did it as a percent, it's going to be pretty unlikely. It's going to be, let's do these as percent. I got it as 0.15%. Okay. And similarly, what's the number of ways you can get one woman? 10 choose. We're selecting one, right? And then we're not done. We still have to select the men that accompany that one woman. So that's going to be what?
8 choose 5.
It's always going to be over 18 choose 6. And that's going to be, it's going to be 3.0%. All right. If you randomly selected juries, you would 3% of the time you would have no women. Oh, sorry, just one woman. What about 2 women? And so let's just do the rest of this. 10 choose 2, 8 choose 4. Yeah, these numbers have to add up to 6. 18 choose 6. That's going to be. Anybody want to guess? Give me a
Oh,
guess.
wait, so let me think. Hold on.
I don't want you to do it. I just want you to guess. You're too slow.
4.5.
Krishna, we heard you typing in your calculator.
Oh, no, but it's wrong. I think that's the right answer.
It's actually, if you round it to the nearest, 17.0%. 17% of the time. What about 3? 10 choose 3 times 8 choose 3 over 18 choose 6. Any guesses? Give me a guess, Krishna.
24.
36% of the time you will have 3
course.
women. 10 choose 4 times 8 choose 2 over 18 choose 6. Give me a guess.
64.
30.
Oh, it went down.
Yeah, it goes down. 31.7. This was 36.2, I guess.
That's what I was going to guess.
There you were? Okay. Okay, so he'll give me the next one then. 10 choose.
Oh, I can't guess that one.
I'm going to guess there's 60%.
So it's 10 choose 5, sorry. Times 8 choose 1 over 18 choose 6. Somebody give me an answer.
I'll say 16.
10.9%.
Oh.
I was closer, Sahil.
And lastly, chances of all 6 people being women.
4%.
3%.
It is 0.11%.
Oh,
Exactly.
So pretty small.
took the words right out of my mouth, sir.
Okay, so do you guys have this little chart on your version?
No.
You don't see anything.
No.
Oh, do you have room to make one? You don't have to,
Okay.
but let's just. Okay, so I'm just going to make this. I don't know why this is not printing out on you. So there's number of women, which is our variable, and this is going to be goes all the way up to like percentage, right? So it's going to be let's make this 40%. Let's make this 30, 20, yeah, 10, 20, 30. So 0 is going to be at 0.15, so like very, very small, like that. 1 is going to be 3%, which is like that. Two is going to be about 17%, which is going to be 15, maybe around there. Three is going to be 36%, way up here. Four is going to be 30, let's say 32%. Five is like 11. And 6 is very small, 0.1. Okay, so that's what your distribution probability distribution looks like from 0 to 6. Those are only outcomes, and either as a chart or a graph or a table. Okay, are we good?
Yes.
You don't have to do this. I mean, it's good to have it in your notes, but you don't. I mean, if I ask you on a test to, I don't know again how we're going to do this on a test
On Google
because
Forms?
yeah, it's going to be hard to do it on Google Forms. So anyway, in a
So
perfect.
you can like link it to like an Excel spreadsheet,
Oh, wow.
and like we can make it on an Excel spreadsheet. I'm just giving you some options.
Okay, well, I'm going to come. I have a few days to come up with something. All right, let's move on.
Okay.
Do you have something like this for the second page? What is the
So we
expect?
don't have the top one. Oh, never mind. I got
The
the
top question is on our first page.
Really? But
That's
do you have
on
any?
the
Why does it
page.
print? Why? Like this is the exact same file I sent you, so I don't know why it prints out so weird. Because you're opening it up with Google Docs, right? I guess. Yes, you open it up with Google Docs and print it, and I don't know why it prints out. So, do you have space then at the top of this page?
Yeah, there's
Yeah, there's a lot of space.
Okay, so you can put something like C question on previous page. I don't know what you want to do. All right. So what is the expect? You guys remember what expected in general?
Yeah.
What's
Is it P times P over N?
yeah? That's
So Q third.
N times P?
Don't use any of the previous ones we've used in 7.2 and 7.3. Go back to 7.1. There was a general formula. If you look at your notes from 7.1, I'm going to get it out. What was your formula for expectation? I got my 7.
7.1.
So if you have 7.1, which I have notes right here, the general formula for all probability distributions is outcome 1.
No.
Let's say outcome 1. Let's say that's not an I, it's a 1 times the probability of outcome 1.
Or the sum of all.
Yeah, plus outcome 2 plus times the probability of outcome 2, and then dot 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 dot. Right. So that's the general formula, and another way of writing that is equals the sum, that big sigma thing, of outcome I times the probability of outcome I, and where I goes all the way from 1 to n. So these two things are the same. Okay. So let's just do that. It's a pain in the butt, but let's just do it. So we have 6 outcomes. First outcome was 0, right? First outcome was, where's my sheet now? Excuse me. The first outcome was 0 times the probability of that. So it would be times 0.0015, right? Times, plus. Next outcome is 1 times 0.03. I guess I'll put all the digits, 017, plus another outcome is 2 times 0.16968. In your original chart I gave you these as decimals, but here I am just putting them as, not as percents, but as decimals. So next one was 3 times 0.36199, and then plus 4 times 0.31674, plus 5 times 0.10860, plus 6 times 0.1131. It's a pain in the butt, but you do get an answer. The expected value, well, you would expect, you would expect it to be around 3, right? Because that's the kind of the peak here. And the answer is, what is the answer? The answer is 3.3 women. So if you randomly selected 6 people and did it, millions of times, on average, from this group, the average number of women would be 3.3. Is there an easier way? Yes.
Always.
Or easier way. Again, it's specific to this distribution, right? So
you can't use that easier way for the other distributions.
Yeah, each distribution has its own easier way. Okay. This first formula applies to every single distribution. But the easier way, there's an easier way for binomial, there's an easier way for geometric, there's an easier way for hypergeometric. Okay, so the easier way is expectation equals just how many people are we selecting for the jury? 6?
5. Actually, I don't know.
The jury is 6 people. And what is the average probability of selecting a woman? Or let's say the initial probability of selecting a woman. How many? There's 18 people altogether.
0.6.
10 out of 18.
10 out of 18. So,
never mind.
So that's the easiest way to do it. Just this gives you the right answer. 6 times 10 over 18. That gives you 3.3. All right. So let's generalize the formulas. The probability of the X successes in N in R dependent trials is probability of X successes is just it was a combination, right? We selected, and what did we select from? We selected initially the number of women, right? So A is the number of successes. I don't like the word successes. If our variable, I guess it's okay to use the word success. But in our previous example, the success was being a woman. That was our variable, the number of women. So the number of women was 10, but here we just call it A. So you're gonna have to get used to these designations. A is the number of successes, whatever it is that we're in our previous example, the number of women, how many women were there? And we are choosing an X number of women. So we did it 5 ways: 0 women, 1 woman, 2 women, 3 women, 4 women, 5 women, 6 women, 6 women. So that's the first part. And then we had to multiply that by, that was the women, then we had to multiply it by the probability of the number of waging and select the remaining, the failures. In this case, failures is men. Successes is women in this particular case, but don't read too much into that. Okay? So it's going to be, if we have I'm just going to copy down the formula, and we'll talk about it in a second. So n minus a over r minus x all over NCR. It's exactly what we just did, but so if it, for example, if you want 5 women, let's say, and this is hard to explain. Anyway, this will come clear once we use the formula. It's exactly what we just did, right? And then the expectation is simply R times A over N. And that's what this was. And the first part was what we did on the previous page over here. Okay, let's just do 2 examples and we'll call it a day. A box contains 7 yellow, 3 green, 5 purple, and 6 red candies jumbled together. 5 are selected at random without replacement. So the words without replacement means it's going to be a hypergeometric and not a binomial. It should be what? What is the probability that exactly 3 are purple? So let's just look at this. We have 7 yellow. We have 3 green. We have 5 purple and 6 red. How many altogether?
21.
21. So the probability of 3 purple equals what? Let's just do it together. You're going to have a numerator and you're going to have a denominator.
3 over 21? Oh wait, never mind.
Oh, we're going to have to use this, right? We're going to have to use this. So this is complicated. Don't even bother using. Just think. I have to select 3 purple. Just think. Select the purple. Whatever. Select the purple candies first.
21 choose 3.
Nope. How many purple
5
candies?
choose 3.
Yeah, it's 5 choose 3.
Oh no, I'm so sorry. I knew it was 5. I looked at the wrong number.
Okay, so and again, you can write it with the brackets, or you can use the C notation. I like the brackets, but you guys seem to prefer. So we have 5 purple candies. We're selecting 3, but now we still have to select how many other candies.
2.
Out of what?
21.
No. That's the total number of candies. But how many candies aren't purple?
16.
Oh, 16.
16.
Yeah, right? Right, so we're choosing the purple ones. And then that's ways of selecting 5 purple candies, ways of selecting 2 non-purple candies over how many ways? What's the denominator going to be then?
21
Yeah.
choose 3.
How many?
5.
5.
Right. Okay, that gives you your answer, and that's going to be 5.9%. All right, why don't you do the next one? What is the probability that at least one is yellow? Try that one on your own. So the
So I'm
probability
gonna get this right, okay?
are greater than 1 yellow. If you're watching this video at home, you can just skip forward a little bit as we wait. Okay, so does anybody want to help me with this?
Would it be 7 choose 1?
Yes.
That at least one is yellow. So it's not just. You're not just.
Or at least 1.
So the problem here is the word "at least" makes it more complicated. So you could have. How many were we selecting here? We're selecting 5, right? Yeah, we're selecting 5 candies. What's the probability that at least one is? So it's either we have to find a probability of 1 yellow, 2 yellow, 3 yellow, 4 yellow, and 5 yellow, and add them all together. Is there a better way?
Do you add them? Or do you multiply them?
Sure.
You would add them, yeah. You find the probability of 1 yellow plus the probability of 2 yellow plus the probability of 3 yellow plus the probability of 4 yellow and plus the probability of 5 yellow. But is there a better way? Yeah.
Can you do 1 minus choosing 0 yellow?
Yeah. A lot easier. Would you rather just do 1 subtraction or 5 additions?
1 subtraction.
Yeah. So let's just do. So what's the probability of no yellow? Again, this is the sort of stuff we did in the probability unit. So I mean, you know how to do this even without this. You don't have to memorize this formula really. Because it's.
Wait, so if you were to do the addition weight, you would do 7 choose 1, 7 choose 2.
Yeah.
And how far would you keep going?
All the way up to 7, choose 5, because you're selecting up to 5, right? You're selecting 5 candies, and there's yellows. There's 7, so you can select all 5 being yellow. But let's not do it that way, because that takes longer. So no yellow is. What's the probability of no yellow? How many yellow candies we have?
It's 1.
Hmm?
Never mind.
Nope.
7 choose 0.
Yeah, we're not. We have 7 yellow ones. We're not choosing any of them, but we still.
Yeah, that's for that is 0. I 1, I think. 7 choose 0.
Okay.
That's 1.
Yeah, that's just a 1. Yeah. What's the second part though? Even though this is a 1, what's more important is this over here.
14 choose 5.
14 choose 5, right? There's 14 non-yellow ones, right? Yeah. If you take 21, subtract 7 is 14, and we're choosing 5 of those non-yellow ones. Over, what's the denominator? Same as I had before. 21 choose 5. So this is going to be. If you punch that all in, you guys can do the work. I mean, you guys have these calculators with these buttons on it, so it turns out to be. Does anybody want to hazard a guess? The probability that at least one is yellow?
90%.
Yeah, you did it, right? Or was that just a guess?
I did it. So.
Okay, 90.2%. All right. Let's do C. What is the probability that none are green but exactly 2 are red? None are green but exactly 2 are red. So let's write that as probability of 0 green and 2 red. Well, this one shouldn't be too bad. Does the fact that you have no green and 2 red, does it make it more complicated than let's say this?
You would do 0, no wait, 3 choose 0.
3 choose 0. How many? So you're doing 0 green. Oh, I see. 3 choose 0. Okay. Then what?
And would you do 6 choose 2?
Okay. Okay. So 3 choose 0 is the greens. In my answer key, I didn't write 3 choose 0 because I
That's
guess
just 1.
that's just 1. But I guess you're right. 3 choose 0. Okay. I didn't write it in my answer key, but I guess you could write it. 3 choose 0 for the greens, and then how many reds do we have?
6 choose 2.
And then is there anything else?
Oh, and then you need to do the rest.
Yeah.
3 left that we can choose.
You have to choose 3 from how
12
many?
choose 3.
What is it?
12.
Yeah. So there's 12 non-green ones and non-red ones, right?
And
Which would
21
be
choose 5.
over 21 choose 5. So that's just going to be, again, you could work that out. Anybody want to hazard a guess?
52.
16.2%.
Never mind.
Okay. What is the expected number of purple candies?
Wait, E. Purple make 6.
So, again, how many are we selecting? R is how many we're selecting. The number of dependent trials, but how many candies are we selecting? If you look at the question, how many candies are we selecting?
We're selecting 5.
Yeah, we're selecting. So the formula is, let's just put the formula R times. Alright, so we're selecting 5, and then what A over N is this is basically, I'll just put it over here, this is basically probability. I was going to put average probability of a success. Probability. How come I can't spell it? Of success. Alright. So what's the average probability of getting a purple? Like, basically, look at the initial probability of getting a purple. That's even better. Initial. So, what's the initial probability of getting a purple? Well, how many purples are there? How many purples are there?
5.
Out of how many?
21.
That's all it is. So on average, you would expect 1.19 purple. If you chose 5 candies. Yeah, so 1.19 of them would be purple. What is the expected number of green and yellow candies?
So we don't have that question.
Oh. Is there enough room to write it? We don't have to do it. If you don't want to write this, if you don't have room or anything, don't worry about it. We'll just do it, and if you want to write it down, if you have space, go ahead. But yeah, a little curious as to why we're having different versions, but that's okay. So, anybody want to give me an answer here? The number of combined green and yellow candies. So what's the first number that we're going? What's the first number that we're going to write? What's the R? R is still 5. We're still selecting 5 candies, but now, out of 21 candies, how many of them are green and yellow? Green and yellow. 10. Right? Right? So that's going to be equal 2.4 green and yellow. All right, I think that's it for today. It's not a tremendously complicated section, so I'm going to stop recording. Let me stop. Hold on. Where's my recording buttons? How come I'm confused now?